Most of the students think particle size is just a number, D50. I thought the same. But in real formulation works, two powders with the same D50 can behave like completely different substances. And that single misunderstanding can ruin your dissolution, content uniformity, flow, and even stability. In this video, I am not going to make you memorize definitions. I am going to show you how particle actually behaves and why formulation fails at the particle level. Let's break the illusion and start with the slide 2. When we study for exam, we memorize three terms: D10, D50, D90. Then we focus mainly on the D50 and assume if the medium size is right and everything fine. That mindset is created by the exam, not by reality. In the real world, two powder with the same D50 can behave in opposite ways. Why? Because particle size distribution is not a number, it's a population, and population have behavior. No manufacturing process create identical particles. Crystallization, milling, spray drying, and all of the produces a range of sizes of particle. So when you receive an API, you are not receiving a uniform powder. You are receiving a crowd of particles. Some particles are small, some are large, and some are between them. And this crowd decides how fast your drug dissolves, whether every tablet has the same dose, whether the powder flows, and how fast it degrades. You don't know design tablet. You manage particle behavior. Dissolution depends on the surface area. Smaller the particle exposes more surface to the medium, and more surface means more dissolution. And now notice something important. Solubility answers the question how much can dissolve, and dissolution rate answers how fast it dissolves. A drug can be soluble and still perform poorly if its particles are too large. This is critical for BCS class 2 drugs, low solubility, high permeability. Here, dissolution becomes the bottleneck. That's why micronization exists, not as a luxury, but as the necessity. Imagine a tablet of 250 mg that contains only 10 mg of API. That means API is just about 4% of the tablet. Now imagine your API particles are very widely in size. One tablet may capture very few large particles, another may receive mostly fines. Why does this matters? Because one large particle can contain mass of thousands of small ones. So some tablet become overdose and other becomes underdose. This is not a mixing problem, this is the geometry. Content uniformity fails at particle level. Below about 50 microns, particles stop behaving like sand. They start behaving like dust. Cohesive forces dominate below 50 microns. Particles stick to each other and to surfaces. So, powders, bridges, sticks to hopper wall, enter dies inconsistently, result weight variation. Now, stability. Smaller particles have higher surface area. Higher surface area means more exposure to moisture and oxygen. That means faster degradation. So, PSD silently attack the both manufacturing and shelf life. D10 means 10% of particles smaller than this size. D50 means medium, not average. 50% smaller, 50% larger. D90 means 90% are smaller particles. Now look at this formula. Span equals D90 minus D10 divided by D50. Span does not tell you size, it tells you how wide the distribution is. Low span means particles are disciplined, high span means chaos. D50 tells you where the particle sits. Spans tells you how dangerous it is. Both particles here have d50 equal to 50 microns. On paper, they look identical, but powder lives in a narrow window. Powder A lives in narrow window and powder B stretches from the dust to stone. One behaves predictably and the other behaves like rat. This is why D50 alone lies. 3 myths students destroy formulations. First, D50 is enough. Second, PSD is only the supplier problem. Third, dissolution equals solubility. Reality is harsher. D50 changes during milling, blending, compression. Particle fracture, fine generates, distribution shifts. PSD is live. If you ignore it, it mutates. In industry, PSD is a critical material attribute. It's appear in regulatory submissions, supplier agreements, control strategies. Companies don't hope PSD behave. They control it because regulators don't forgive particle chaos. Now let's move from theory to reality. You receive 2 API batches from supplier, same drug, same chemical purity, same D50, 60 micron. On paper, they look identical, but their distribution are different. Batch X is narrow, batch Y is extremely wide. Before I show you anything else, pause and think. Which one would you trust in real formulation? Don't answer emotionally, think physically. Which powder will behave predictably inside a blender, a hopper, a tablet trace? This is the exact decision formulation scientists make in the industry. Let's calculate span. For batch X, span equals 70 minus 50 divided by 60. That gives us about 0.33. For batch Y, 190 minus 5 divided by 60. That gives us almost 3. These numbers are not a small difference. They describe two completely different materials. Batch X is a disciplined and batch Y is chaotic. One behave like a controlled system and other behave like a gamble. Batch X has a particle clustered tightly between the 50 and 70 microns. So, dissolution is consistent, mixing is predictable, flow is stable, degradation is moderate. Batch Y contains both dust-like fines and rock-like large particles. Some tablets dissolve fast, some dissolve slowly, some get overdose, some get underdose, some flow become erratic, stability worsens. Same drug, different fate. This is what PSD really means. Let's understand the physics. During blending, fine particles stick together and form agglomerates. Large particles sink due to gravity. During dye filling, fine sticks to hopper wall. Large particles drop unevenly into dyes. Now combine this with a low dose. When 2 API is only 4% of the tablet, even one extra large particle can shift the dose. This is why content uniformity fails. Not because of poor mixing, but because of physics always wins. You cannot mix away gravity. When PSD is wide, industry has 3 main tools. Milling. It reduces the large particles, but it also creates fines. Sieving. It narrows the range but wastes material. Granulation. It hides PSD inside granule but adds cost and complexity. Every solution is a trade. A good formulator doesn't ask, how do I eliminate the problem? They ask, where do I pay for it? If you had to choose one batch for the development, the rational choice is batch X. Why? Because it gives you predictable dissolution, easy manufacturing, stable quality, regulatory peace. Batch Y gives you processing burden, high risk, justification nightmares, scale up disaster. Professionals don't start with a bad material and try to become heroes. They start with a good material and build a stable system. Particle size distribution is a population, not a number. D50 without span is meaningless. Wide distribution causes segregation. Segregation destroyed content uniformity, and at the end of the chain, particle decide performance, not equipment, not formula, not for only particles. Formulation doesn't fail in the tablet phase, they fail at the particle level. If you understand the particles, you control the tablet. If you ignore them, the tablet controls you. This is the real meaning of particle size distribution. Thank you.